Welcome back to the Twilight Zone. Today, we're going to discuss a lab for my Chemistry 104 class, which is second semester chemistry. And the lab that we want to perform, and that I really would love to have you do this one hands-on, but we are preempted by the coronavirus. Because it's a very simple lab to do hands-on. The real challenge comes with processing the data. What do you do with the numbers when you get them? That's where we're going to spend most of our time. But I'll follow a similar format. I'll give you some background, the theory behind the determination of the formation constant for a complex ion. Then the method for gathering the data, and then we'll use that theory to process the data and get the answer. And the answer is the formation constant for this species. Right? So that's a complex ion. And it has a name. Now, I didn't give you all the rules for naming complex ions, but if you ever need to look this one up, it's called diamine silver 1 ion. Right? What that means is that you have this ion in solution, but remember, solutions are always neutral. Actually, very few instances in chemistry you will find an unbalanced charge. It's possible to obtain it, but it's not desirable usually. So there will be a counter ion for that one, and it could be anything. In our case, it's probably chloride. Right? So you would have one chlorine out here as the counter ion. All right. So we want to find the formation constant of this species, right? And how does that species form, right? So the species forms with a silver ion in solution, and then we add ammonia in solution, right? And it produces that ion. It produces this. Okay? So notice, since this is neutral, and right, to balance it, we need two of these. Right? So this is the overall equation for the formation of that ion. In reality, the process of forming this ion is 2 steps. In other words, the silver picks up one ligand. That's what this is called, the ligand. It picks up one ligand and forms an ion with only one ammonia. But the equilibrium for this reaction drives it further to pick up a second one, right? And we want the Kf for the overall reaction. Okay? So this is the reaction that we're focusing on, and that's where we begin. All right? So if you haven't guessed already, this whole process is an equilibrium process. I remember, if you thought that when I introduced equilibrium uh, early in the semester that that was going to be the end of it. Well, you guessed wrong. Equilibrium pops up continuously from now to the day you die. So what's the equilibrium expression for this one? The formation constant is an equilibrium constant, K, right? It just has a different subscript. Remember when I talked about subscripts, they each have different meanings. You could have a KEQ, which is just a general equilibrium constant. You could have a KSP, which is a solubility product for a special situation. And we'll actually need one of those in this process. You could have a K sub P for equilibrium expression, which uses only partial pressures of gases, right? So the subscript has meaning. And in this case, our KF expression for that equation is, remember, the equilibrium concentration of the product divided by the reactants. Right? So if we follow our rules, then we'll have ammonia concentration. Oops, that's a boo-boo. Square brackets for equilibrium squared because of that coefficient. Okay? So this is the equilibrium expression. If we could derive each of these terms from our hands-on lab, then we could solve that directly. But it's not that easy. Formation constants, because there are no insolubles produced in this process, it's difficult to know where the endpoint is, where the equivalence point is, where the equilibrium point is, to be exact. So we need some help, right? And here's the way we're going to do it. Remember, dig way back into the dim reaches of your mind, and remember if you had the General Chemistry 1 lab set, we had a lab that we did called Le Chatelier's principle. And in that lab, we had several examples of equilibrium that were disturbed in Le Chatelier's world. They were disturbed by the addition of some other species into that solution, which was not part of the equilibrium expression. It was a separate entity, but it had an influence, an impact on the equilibrium equation. Remember that? And I said those reactions, there were two of them, were linked, right? And the reason that the equilibrium expression for the disturbed equilibrium was moved in some form or fashion was because of that linked reaction. Right? This is another example. We're going to link two reactions in solution, and we're also going to link them by formula, by an equilibrium expression, so that the calculations become easier. Right? If we only have one expression to deal with, the calculations should be easier. Right? And I hope that will become evident as we proceed. Right? So this is our equilibrium expression, and that's the value that we want. This is the target. Okay? But we're going to link a second equation, or second reaction, excuse me, with its corresponding equation. And all of this is explained in the hard copy, right? This is what your hard copy looks like. You'll find it in Blackboard, right? And it's nauseatingly detailed, Right? We're going to cover all of this stuff right here. So you're going to see it here on the video, and you're going to have a hard copy to deal with. You'll also be given a data set, a very simple data set, just 4 numbers, actually 3 numbers that you determined from the experiment, and then the 4th number I went ahead and gave to you. Okay, so you have the data, you'll have the hard copy that you need to print off, and you'll have the video in Blackboard. And as soon as I finish it, I will notify you. What else will we have? You'll notice that, just a caveat, the method calls for 2 different titrations. You remember titrations. You better remember titrations. We actually have 2 data sets here that are available. We're only going to use the first one. Right? Just ignore the second one. It's been my experience that the second one never works very well anyway. So we're just going to do the calculations based on 1 titration. Okay? So what's that other reaction that we're going to link with this one? Well, think back to our Le Chatelier's principle, and what type of reaction did we use with silver? Right? We had silver nitrate in solution, and we added to it, I think, maybe potassium chloride. Right? So when you add those 2 together, the silver ion and the chloride ion combine and form an insoluble product. Right? It precipitates. If you wait long enough, it'll settle on the bottom of the container. But in the beginning, it precipitates by forming a cloudy white silvery color. So we're going to link that equation that we just described with this equation. And let me see, I want to get it in the correct order. Okay. So this one is in the form of this plus that. Right? So you'll recognize this as a solubility problem. That's a solid. And for quantitative purposes, we say that silver chloride is insoluble. But we know from experience that there's always a little bit of that goes into solution. Not much, just a little bit. And the expression for that is in the terms of its solubility product. Now you remember why we call it a product? Because solids and pure liquids are excluded from the equilibrium expression. Right? So that being said, you only have this part in the expression. Right? What does that look like? It's a product. That times that. All right? So this has a known value. Right? This is the unknown. This one is known. And it's given in your method, I believe, as 1.7 times 10 to the minus 10. Okay? So how are we going to combine these so that we can use this reaction? Well, the first thing you have to recognize is that if you add these components together with these components, they're both in the same neighborhood, right? So they have opportunities to interact. So whenever this concentration down here is known, it's the same concentration as that one. Why? Because they're in the same neighborhood. They're in the same Erlenmeyer flask in our case. Right? So when we combine these two, how are we going to combine them? Well, the way we do it is we solve this one for silver and substitute the equivalence of that silver expression in here for that silver, right? And that's given in your method. And I don't have a lot of room here, so I'm not going to do all the math and substitution. But once you solve for this one, you get that one divided into this one. And that goes into this expression. All right? So here's what it looks like. I guess I will give you some detail. So if we solve the silver for the KSP and substitute it in here, what we get is this stays the same. And this becomes, over here, we have KSP for silver divided by chloride. Okay? All we did was substitute that in for this value. Now, when we actually do the titration, and if we solve this, then remember the denominator of the denominator is a numerator. Right? So this one moves up here, and that says this complex ion times the concentration of chloride divided by KSP times ammonia squared is the expression that we're going to use to solve for K, the case of F. All right? So, pause for a moment. So, notice that silver is not part of this expression. So that implies that during the titration process, we have converted all of the free silver into the solid silver chloride. How do we know that? Well, we know that because it forms that precipitate that you've seen before. Only it's very, very faint, right? Before, in Le Chatelier's lab, we just made a lot of it so you could see it easily. But we want to find out exactly when it forms. That's our endpoint. Right, so let's talk about the method itself. So we'll come back to this in just a few minutes. And in fact, I'm going to need to make a little bit more room here. And just erase that too. All right. So, in this experiment, if you were doing it hands-on, you would need a volumetric flask of exactly 100 milliliters. A volumetric flask is calibrated so that you know exactly, within certain experimental error and with error that's defined by the glassware itself, you would know exactly that you would have 100 milliliters in that flask. And there's a mark on it right here. somewhere on that neck. And all you have to do is be sure that your final volume has the meniscus sitting on the bottom, right on that mark. Right. Why do we need this? We need accuracy. We need to know exactly the concentration of whatever solution we put in it, right? So we're going to prepare a solution. The first one is silver nitrate. Right? So we're going to prepare a solution with 0.1 molar silver nitrate. And we're going to put 5 mils of that in this flask and dilute it to 100 mils. So you can calculate the concentration. You know how to do that. M1V1 equals M2V2. Right? So you can calculate the exact concentration of silver. You don't care about nitrate, it's a spectator. All you care about is silver. So what's the concentration of silver? Well, if it's 0.1 molar silver nitrate, it's 0.1 molar silver. So you put 100 mils of 0.1 molar silver in there. You put 5 mils of silver nitrate in there and dilute it to 100 mils. Then you know the concentration. Right. So that gives you a known concentration of silver. And then we're going to add, actually in that same flask, we're going to put 5 mils of 1 molar ammonia. Right. The bottle will say ammonium hydroxide. But in fact, on the last page of your hard copy, I give you a calculation in the appendix that proves that 99.6, at that concentration, 99.6% of the ammonia is not ionized. It is ammonia in solution. It's not ammonium. Right? So we're safe in saying that we have that concentration. You work out 2 different concentrations, one for ammonia, one for silver. Right? And we'll walk through those concentrations in just a minute. Right? So once you get this solution, then you transfer it into an Erlenmeyer flask. 125 milliliter Erlenmeyer flask. So it all goes in here, and it's going to be in the neighborhood, maybe here. And we're going to put a stir bar. What a stir bar is, it's a little magnet that's coated in Teflon. So it doesn't react with the solution, but it can be stirred remotely through magnetic coupling. Right? So you have a bigger magnet down here that's spinning, and it keeps the solution agitated. You don't want to vortex it. You don't want a vortex in there, right? Because that adds bubbles. We want to be able to see the development of the silver chloride without interference from bubbles. So don't vortex it. I'm talking to you as if you were actually doing this hands-on, because when you write your formal report, it needs to be in that format. Right? When you write the procedure, you write it as if you did it hands-on. That means third person, passive, past tense. This was done. Right? The reason I hammer that so hard is because no matter how many times I grade you off on doing it wrong, you still do it wrong for subsequent formal reports. It's maddening. So we transfer everything into that flask. Now we're going to titrate what into it? Potassium chloride. That's where our chloride ion is added from, is potassium chloride. And that will be a volume that is unknown at this time. Right? That's the whole point. We want to find the volume of chloride that needs to be added to just barely develop the first hint of silver chloride. Right? So we have a burette. Right? The valve. Right? You know how burettes work. Right? You can read them down. They're calibrated for tenths of a mil, but you can interpolate between the marks to get some fraction of a tenth of a mil in the hundredths. Right? So we add our potassium chloride, and the potassium chloride is what concentration? It's 0.1 molar. I would have actually prepared a solution that is as close as I can get to 0.1 molar. And these solutions are really close, really close. So you don't, I took that variable out of the scenario. The only variable you have is how you prepare the solution and then how you do the titration. So how do you know when that silver chloride appears? Right? It's very difficult to see in the bright lights of most rooms, labs, workspaces. So what we do is dim the lights and just let the ambient light come in from outside, just so we can see what we're doing and be relatively safe. And how do we know when silver chloride develops? Well, we use an ancient effect by our standards, 19th century, early 19th century, by a scientist by the name of Tyndall. It's called the Tyndall Effect. And it's used, typically used, to distinguish between a true solution and a colloid. Right? We talked about colloids. Colloids are persistent suspensions, right? Because the particles are so small, between 1 and about 1,000 nanometers in diameter. So they mimic solutions in that respect. In other words, they don't settle out. Good example of a colloid, Jello. So what is the Tyndall effect? Well, as you do the titration, you'll notice periodically something develop and then go away. Remember when we did acid-base titrations? Right? It was clear to start with, but with the phenolphthalein in there, as you added the base, the pink color developed and then went away. And the closer you got to the end point, the more persistent the pink was before it disappeared. And when you reach the end point, that persistent faint pink remained. Use that for this. The opalescent, they call it, kind of a silvery, shiny, whitish tinge to the solution. It develops and then goes away. Right? Whenever a drop of this hits that solution, you see it. It's very pronounced. You see that opalescence appear and then go away. But it becomes more persistent as you get closer to the endpoint. And at these concentrations, that endpoint comes really quick. It's like within a 1 milliliter of addition. So you add a small drop at a time. So as you add your drops, it's easy to see that, but we want to know when the faint, persistent opalescence remains. And the way to see that is with the Tyndall effect. With suspended solids or colloids, the Tyndall effect is such that you shine a light right? And that light beam shines at right angles to your eye through the solution. When it's a solution, you don't see the beam in your flask, right? There's nothing there. But with a suspended solid or a colloid, you do see the beam. And it's easier to see that beam going through your flask if the lights are dimmed. So that's why we dim the lights. You see, when that persists, then that's your endpoint. And you take the volume, right? If you started at 0, you just read it off your burette. If you started anywhere else, you subtract that from the volume that you read, right? You all know that. So now you have everything you need. You got this concentration, that concentration, and you have the volume added to reach the endpoint. Those are the 3 data points that are given in this document right here. Okay? This volume, and that volume are given. And then the total volume is this volume. How much volume is in that flask after the titration? You need to know that. Well, the amount of volume in that flask is 100 plus what you added to it, right? There's no mystery. Why do we need to know that? Because the Kf is an equilibrium constant. Equilibrium depends upon concentrations. And this concentration is not equilibrium. That concentration is equilibrium. So you're going to use these values to calculate what is the concentration of each one in that flask when you reach equilibrium. Okay? So it's really not important that you calculate the concentration over here. You want to calculate the concentration in there. And we're going to build an ice table with that information. Right? So let's see. I think we can go to that place right now. Okay. Always a problem. The problem is our Kf expression has another constant in it, and ice tables don't deal with constants. Right? You don't put a variable up here that is not a variable. In other words, you can't put a constant up there on your ice table. So what we have to do is modify our K expression just slightly so that we can use it in an ice table, right? So our Kf expression now becomes, we're going to substitute, what does Ksp mean? Ksp for silver chloride is the concentration of silver times the concentration of chloride. So instead of Ksp in that expression, we're going to plug in actual concentrations. Right? So this is what it looks like. Now that seems strange, doesn't it? To have 2 chlorides in there. Well, they are different because this is product and this is reactant. So that's the chloride concentration as the reactant. This is the chloride concentration as the product. Right? So when we build our ice table, it's going to look like this. Right? Now I'm going to try to squeeze these in. Let's see, let me move it down just a little bit. I think I can do that. Let's write these in first. So our ice table is going to be, that's product, so these are reactants. So I'm going to put silver first. Right. Then ammonia. Then chloride as the reactant. Then I'm running out of room. Okay, hold on a second. Let's squeeze them a little tighter. Hopefully the video quality will catch all of this. Okay. And then we're going to have the, I'm going to use complex ion. How about that? That's what that means. Complex ion is that value. Don't get it confused with chloride. That's complex ion. And then the product chlorine. All right. So our ice table is going to look like this. Now, remember what I said. We needed to know the concentration in the Erlenmeyer flask in order to do this calculation. But that can get pretty unwieldy. It's easier at this point to use absolute, actual amounts. And then once we've got the actual amounts at equilibrium, we calculate the concentrations. Right? So remember what I said, when you've got a concentration of molarity, that's moles per liter. But for convenience, since we don't want to have to change milliliters to liters each time we multiply, right? To get the number of moles, you need molarity times volume. Right? Well, if we multiply molarity times milliliters, then we don't get moles, we get millimoles. Right? So millimoles is easier to deal with for our calculation. And that's what we're going to do. So in this example, the volume of silver added was 5 milliliters. So 5 times 0.1 is 0.5 millimoles. So this is our initial concentration of silver. Millimoles. Okay. Ammonia, we added 5 milliliters of 1 molar. So this one is 5.0 millimoles. We started off with, let's see, well, the chloride that we added initially during the titration would be a value that you're given here. But let's just say, for argument's sake, and keep the numbers simple to deal with, we added 1 milliliter of potassium chloride, and the concentration of potassium chloride is 0.1 molar, right? So since this breaks up into that and that, if we have a 0.1 molar solution of that, we also have 0.1 molar solution of chloride, right? So the chloride ion is 0.1 times what volume? 1 milliliter. So it's 0.1 millimole. That's what we start with. Now this is 0, right? Because this is an initial, right? This is, we've added it to the flask, but it hadn't reacted yet, right? So that's, you have to think Twilight Zone. It's all in your head. Before anything happens, this is what it looks like. The concentration of a diamine silver ion in the beginning is 0, right? Because it hasn't reacted yet, right? We put it in the flask and then we titrated it, but we're saying to ourselves, yeah, but I'm going to mysteriously keep it from reacting. So we haven't produced any complex ion or chloride on that side. Okay. So what's the change? Well, when we reach the endpoint, all of that silver that we started with is now gone. It's converted to the opalescent color. So the change is we're using it up. It's gone, right? So that means 0. Ammonia, in order to do this, we had to use let's see, pause for a second. Okay, so look at the ratio. If we use up the silver, to form this ion, let's see, that needs to be a plus there. To use up, if we use up the silver to make that ion, how many millimoles of ammonia does it take to match 0.5? Well, it takes twice as many, right? There's 2 of them for every one of these, 2. So that means we're going to use up that much of this added amount. Actually, we don't need that right now. And then we're also going to use up all of the chloride. Remember, we've got a coupled reaction here. So there are 2 things going on. In the titration, every time we add chloride, it reacts with silver, whatever silver's floating around. But where is it getting that silver? It's getting the silver from here, right? We formed it from here. We're using it up here to go to there, right? So in order to go from here to here, we use up that much. And in order to go from here to here, we use up that much, and it ends up over here. Right? So that means in the end, we have 0.1 at equilibrium. We have 0 here, and we have 4 millimoles there. So each one of these is also millimoles. Oh, how much of the complex ion do we have? Well, for every one of these, for every one of those, you get one of these. So it's the same as that, 0.5. Okay, so now we have our equilibrium in terms of millimoles. Now we have to calculate concentration. Right? So that's where it gets interesting. All right. Remember that in this scenario, we had 100 milliliters from the volumetric flask, plus we added potassium chloride solution to the amount of 1 milliliter. So the total volume is 101 milliliters. Now, if you divide millimoles by milliliters, if you divide moles by liters, you get molarity. If you divide millimoles by milliliters, you get molarity, right? Because the millis cancel out. Right? Milli, mole, milli, liter. Millis cancel out, moles divided by liters. So if you divide the millis by the millis, you get molarity. Right? I just wanted to make that point because that confuses some students. All right, so now we have our equilibrium amounts. We need equilibrium concentrations. So I'm going to have to erase this and put the concentrations up here. I'm going to leave that for now because we might need it. All right. So what's the concentration? Since we had 0 millimoles of silver, it has no concentration. So the next item there is ammonia. The next one over was ammonia. So let's say for the concentration of ammonia, we had 4 millimoles. Divided by what concentration? 100 milliliters plus 1 milliliter of potassium chloride. Which is equal to 3.960 times 10 to the third minus 2. Molarity. Okay? And like I always say, don't throw away any decimals until the very end. Keep them all. That helps you avoid rounding errors. Okay, the second one. What was the second one over? Chloride. Well, the chloride you have now is up here. It's a product. So the chloride product is 0.1 millimoles divided by 101 milliliters. Right? Now your calculations are going to be a little bit different because you're going to have a different amount of potassium chloride. Right? So take that into account when you set up your ice table. That'll give you a different amount of chloride. It'll also give you a different amount of final volume. Okay? So that calculation is 9.901 times 10 to the minus 4 molarity. And then the other is the complex ion. So I think I can write the whole thing out here. And that concentration was 0.5 millimoles per same volume. And that's 4.950 times 10 to the minus 3 molar. Okay? And then the other factor you need, we're going back to the original combined equation where we had the KSP inserted. And remember, the KSP for silver chloride is equal to 1.7 times 10 to the minus 10. Yeah. Okay? So now we have our equilibrium concentrations. Remember, these are all equilibrium. We just calculated them. Do we have everything we need? Well, according to the KF expression that we used before, we need this, we need that, we need that, we need this. We got everything we need. Right? So now the expression that we're going to be using is, this is product, right? So we leave that one intact, and we replace that solubility product with KSP. Right? All right. So now we can calculate the formation constant. All we need is that value, which is 4.950 times 10 to the minus 3 molar times 9.901 times 10 to the minus 4 molar divided by 3.960 times 10 to the minus 2 molar times the KSP. Okay? So when we calculate this one, based on that hypothetical titration, where you only need 1 milliliter of 0.1 molar KCl, we get a value. I'm going to let you do that. Your calculator will do that for you. All you have to do is be sure you put the numbers in right. We end up with 1.84 times 10 to the 7th. Oops. That's not right. Formation constant. All right. So we got that value. What are we going to compare it to? Right? What's the accepted value? Did I put that in here? I'm looking. Well, that's not too smart. Because if I don't give you an accepted value, you can't do a percent error. Hold on a second. Here's what I'm going to do. I'm going to look it up. I've got it right here in my magic bag. There we go. So we need ammonia and silver. Silver and ammonia. Here we go. The accepted value at least from this publication, they vary somewhat depending on which publication you look at. But that's all right. We're only concerned with the method, that you know how to do the percent error. 1.6 times 10 to the 7th. Right? So we're in the same ballpark. Right? So you calculate the percent error when you calculate your value. Right? What does this tell us? What does the KF tell us about the reaction between silver and ammonia to form the complex ion? That is a huge number, which means it's favored toward that product, right? So practically all of the silver, before we titrated it, was in this form. Okay? That's it. That's what it says. Okay. Let's see. Is there anything else? There are no questions in this lab. You don't have any lab questions to answer. All I'm concerned with is that you produce an acceptable formal lab report. Right? And you know how to do that. You've got a rubric to go by. You've got numerous graded examples from Chem 1 and previously in this semester. You know where you always go wrong, and I'm willing to say that most students go wrong in method, and then in interpretations. Right? So there's your example. There's all the calculations. I showed you how it was done. That's the best I can do for you, except without being hands-on, of course. Hands-on would be much, much better. So there it is. Good luck, and I'll have this video up shortly.